Section 3.4 is on systems of equations in three variables. A system of equation in three variables is three equations, each of which can contain an x, a y, and a z. It can have one solution, that is an ordered triple, an x, y, and a z, no solution, or infinitely many solutions. To solve such a system, we want to use two pairs of equations to eliminate one of the variables. Then use those two resulting equations to eliminate another variable, and then substitute. Let's take a quick look at a couple diagrams from your textbook that show what your solutions can look like. Actually an equation in three variables is actually the equation of a plane. Remember that an equation of a line and equation in two variables is that of a line. If there are three variables, you're talking about three-dimensional space, and it's going to be a plane. So if there is one solution, one ordered triple, then that means the three planes intersect in one point right there. If it's infinitely many solutions, then it means that the planes intersect in a line, and that can happen a couple different ways. So here we have three planes that are all kind of intersecting in this one vertical line. The planes can also intersect in the same plane. So in other words, all three equations represent the same plane. Another case that isn't shown here is two of the equations can be the same plane, and the third equation can represent a plane that intersects it in one line. And you'll recall from geometry that the intersection of two planes is a line. And then the third possibility is that you have no solution to the system, and there are no points in common with all three planes. So all three planes could be parallel. Two of the planes could be parallel with one intersecting. You'll notice that even though the yellow plane and the green plane intersect in a line, and the yellow plane and the blue plane intersect in a line, there's no one place where all three planes intersect. And then you can have a situation that looks kind of like this triangular prism right here. So let's take a look at a couple examples here, and this is a little tedious and it's easy to make mistakes, so let's just go slowly. So we have these three equations, and you'll notice they each have an x, a y, and a z, and when I write it I kind of like to keep it lined up so I can see all of my x's in a column, y's, z's, equal signs, and then my constant in a column. So the first thing we want to do is to eliminate one variable from the equations. So I'm going to choose two pairs of equations. So I think, for example, I'm going to start with equations 1 and 2. And it doesn't matter what you choose. I'm kind of liking the y's right now. So I'm going to leave the first equation the same. And I'm going to take the second equation and multiply it, by a -3. And you'll see what that will do to the y's. If I leave the first equation the same, I'll have a 3y, and the second equation multiplied by a -3 is going to give me a -3y. So let's just write those again. So that's going to be 5x plus 3y plus 2z equals 2. And now multiplying the second equation by -3 gives me -6x minus 3y plus 3z equals a -15. And now I'll add those two equations. And that's going to give me a -x. And notice my y's cancel. That's good. I want that to happen. Plus 5z equals a -13. So now I have one equation with just an x and a z. That's good. Now I want to use another pair of equations, two other equations, and eliminate y from those two. So I think I'm going to use equations 2 and 3. Okay, and multiply equation number 2 by a -4 because I have to eliminate my y's. So I'll do equation 2 times a -4, and then I'll just keep equation, and then equation 3 I'll keep the same. So equation 2 times a -4 gives me a -8 minus 4y plus 4z equals a -20. And then equation 3 I'm going to leave the same, x plus 4y plus 2z equals 16. Now I'm going to add those two equations, and by personal preference I just like to set it up so that I always end up adding the equations. I tend to make fewer mistakes adding than when I'm subtracting. So this is going to give me -7x My y's cancel, plus 6z equals a negative 4. And you'll notice this equation here and this equation here, each of them only have an x and a z and a number, and I set it up that way so that I eliminated y from the equations. Now I'm going to take those two equations, write them over here, and actually maybe I could do it under here, and no, I'll do it over here, and eliminate a variable from there. I think maybe I would like to eliminate the x's since I have a coefficient of negative 1 here. So going over here, I'm going to multiply this equation by a, let's do it by a negative 7 times this first equation here. And then I'll keep my second equation here the same, negative 7x. Actually, you know what? I'm going to go ahead and write that one down here. So that's going to give me a positive 7x minus 35z equals a positive 91. And then this equation here that resulted from my second elimination is 7x plus 6z equals negative 4. And now when I add those, my x's will eliminate, and I'll end up with a negative 29z equals 87. And then dividing both sides by 29, I get z equals negative 3. And there's part of my answer right there. Okay, now I need to find x and y. And to do that, I'm going to plug negative 3 into z into any of the equations that just have x and z. Maybe I like this one up here. So I'm going to take this equation that I got from my first elimination, and I'll have negative x plus 5 times negative 3 equals a negative 13. Negative x minus 15 equals negative 13. And adding 15 to both sides, I'll get negative x equals 2, or x is equal to a negative 2. So there's my x. I've got my z, and now I need to find my y. And to do this, I think I'm going to have to go back to one of my original equations here. Maybe I'll take the second one since the coefficient of y is already 1. So we'll have 2 times x plus y minus z equals 5, or negative 4 plus y plus 3 equals 5. That's going to give me a negative 1, and adding that to both sides, y is going to be 6. And so my final answer, I don't know if I have room here, I'll write it over here, is going to be x is negative 2, y is 6, and z is negative 3. And that's my answer as an ordered triple. And this means that there is one solution, that these three planes intersect in one point. As you can see, this is going to take a lot of binder paper. Let's take a look at a second example here. And I have these three equations. And I think, again, just because I kind of like the look of this, I'm going to eliminate y from, I'm going to take the first two equations. So I think I'll take the first equation and multiply it by a negative 2. And that gives me negative 4x minus 2y minus 3z equals, whoops, I did that wrong. Hold on. Forgot to multiply by negative 2, plus 6z equals a negative 10. And I'll keep my second equation. Oh, that was equation number 1. Let me write that there. Equation 1, and I'm just going to copy equation number 2, because notice that has a positive 2y. And I will add these two and get negative 3x. My y's cancel, plus 2z equals a negative 3. Okay, so there's a set of equations where I've eliminated y. Now I'd like to use two other equations and eliminate y. And maybe I'll take the first equation, equation number 1, and multiply it by a negative 3, and use the third equation. So the first equation multiplied by negative 3 gives me negative 6x minus 3y plus 9z equals negative 15. And equation 3 is 6x plus 3y minus 9z equals a positive 15. And when I add those two, look at what happens. X's eliminate, Y's eliminate, Z's eliminate, constants eliminate. I get 0 equals 0. So what does that mean? That means that these two equations, equations 1 and 2, are the same plane. They have exactly the same equation. Okay. In fact, what we saw was if you multiply the first equation by, it would be a positive 3, you would get exactly equation number 3. So those two are the same plane. So what this means is that this plane, represented by equations 1 and 2, intersect this line right here, intersect the other plane in this line right here. Okay, so there are infinitely many solutions. Because equations 1 and 3 are the same plane, they intersect equation number 2 in a line, and that line means that there are infinitely many solutions to this system. Okay, and let's take a look at the last example here. Here we have another system of equations, and I think I'm going to take, I think maybe I'll try to eliminate y again. I don't know why I feel like eliminating y, but I do. So equation 1, I'm going to multiply that by a negative 2, and equation 2, I'm going to leave the same. Okay, so that's going to give me a negative 6x plus 2y plus 4z equals a negative 8. And equation 2 is 6x minus 2y minus 4z equals 11. And when I add those two equations, my x's eliminate, my y's eliminate, my z's eliminate to give me a 0. But over here I have a 3. So there is no solution. In other words, equations 1 and 2 are going to be parallel planes. There's no way that they intersect in each other. So there's no solution to this system of two equations. Okay, and then if you will notice that we're actually, if I were to take equation number 1 and multiply it by 3, so that gives me 9x minus 3y minus 6z equals 12. That's exactly the same as equation number 3. 9x minus 3y minus 6z equals 12. So these two are the same plane. So what we really have in this case is equations 1 and 3 being the same plane and being parallel with equation number 2. Therefore, there is no solution to this. We have two planes that are exactly the same, and the third plane is parallel to those two. So what we saw in this lesson, and I apologize this video is kind of long, is how to solve a system of equation that has three variables. So you can end up with one solution, that is an ordered triple. You can end up with infinitely many solutions, that would be the planes intersecting in a line, and you can end up with no solution where the planes are parallel to each other.